Okay, in section up to section 9.9, we talked about Bernoulli's equation. And Bernoulli's equation is associated with uh, a very smooth fluid flow, like a frictionless situation, an ideal fluid where there's a non-viscous fluid, an incompressible fluid, motion is steady, no turbulence. We've now talked about viscosity and what effect that has. But now I guess we'll be talking about turbulence. Because at sufficiently high velocities, fluid flow changes from simple streamline flow to turbulent flow, characterized by a highly irregular motion of the fluid. Experimentally, the onset of turbulence in a tube is determined by a dimensionless factor called the Reynolds number, Rn, Reynolds number. Reynolds number is the density of the fluid times the velocity of the fluid times the diameter of the tube divided by the viscosity eta of the fluid. And if Reynolds number is below about 2000, the flow of the fluid through the tube is streamline. Sometimes that's called a laminar flow. Between 2000 and 3000, the flow is unstable, meaning that the fluid can move in streamline flow, but any small disturbance will cause its motion to change to turbulent flow. And turbulence occurs if the Reynolds number is above 3000. So in example 9.19, we're going to use Reynolds number to determine the speed associated with the onset of turbulence. Problem: determine the speed at which blood flowing through an artery of diameter of 0.20 centimeters will become turbulent. So first we want to solve this equation for V. V equals Reynolds number times the coefficient of viscosity divided by the density of the fluid, rho, times the diameter, d. So at 2000, it becomes unstable. At 3000, it's almost definitely turbulent. So I'll go ahead and use the 3000. The coefficient of viscosity for blood is in one of the tables that we saw earlier, 2.7 times 10 to the negative third Newton seconds per meter cubed. The density of blood is 1050 kilograms per meter cubed. It's just a little bit denser than water. And then the diameter was 0.20 times 10 to the negative second meters. So the velocity at which blood would become turbulent in this 0.2 meter, that would be equal to 0.2 centimeters would be 2 millimeters. So, and it comes out to be 3.86 meters per second. Now, I'm not sure how that compares. That's probably the size like of an artery or something like that. I'm not sure though. Arteries, veins, and capillaries, I guess you have in your body. But that seems very narrow to me. All right. Now, question. If the viscosity of a fluid flowing through a tube is increased, does the speed associated with the onset of turbulence increase or decrease? And well, you can tell just by looking at the equation, if the viscosity increases, Reynolds number, solving for velocity. We want to solve for velocity. Okay, so if the viscosity increases here, the velocity also increases. Exercise 9.19 is essentially exactly the same question. The only difference is that now, instead of pretending I look things up in the table, I'm going to actually have to look things up in the table. Water at 20 degrees. Eta is 1 times 10 to the negative third. Actually, density of water, I don't have to look that up. I have that memorized, 1,000 kilograms per meter cubed. And then the diameter of the straw is given in the problem as 0.006 meters, which is 6 millimeters across. So we can once again take 3,000 times 1 times 10 to the negative third divided by 1,000 divided by 0.006. And the answer is 0.5 meters per second. So two things, water has the lower viscosity than blood, which slows it down, and it's got a bigger area, which also slows it down, or a bigger diameter, which also slows it down.